Okay, guys, time to work on the next phase of chapter 14. We started this chapter, we talked about the fact that concentration, temperature, nature of the reactants, state of matter, all had a role to play in how fast chemical reaction happened. Okay? So when we look at the rate law and the integrated rate law, we can see concentration effect, but we don't obviously see the temperature effect, the nature effect coming into this. So they're kind of hidden. We want to now look at how nature and temperature affect the rate of a chemical reaction. And this was done by a scientist by the name of Arrhenius. Okay? Arrhenius was able to work out how temperature is connected to K, the rate constant, and how the nature of the reactants is also connected to K, the rate constant. What he did is he worked on doing a series of reactions where the concentration stayed the same, but the temperature changed. So he was able to derive two different equations. One, K is equal to A, E raised to the E sub A over RT. E sub A, he called the activation energy. It's the minimum energy the molecules need when they collide for a successful reaction, a successful breaking of old bonds and making of new bonds. Okay, activation energy. R is the gas constant, but this one's in terms of joules, 8.314 joules over moles times Kelvin. T is temperature, and A is a factor that reflects orientation probability. That's connected to nature. The more complicated the structure, the harder it is to line them up to collide correctly. Okay? The simpler the structure, the easier it is to line them up. Okay? So, as you increase the temperature, because temperature is in the denominator up here in the power of E, you increase K. If you increase K, you increase the rate of the reaction. Now, if we play with math for a little bit, we can take Arrhenius's original equation and get this second equation. The natural log of K2 over K1 equals a minus E sub A over R times 1 over T2 minus 1 over T1. Okay? And this becomes a plug and chug equation. So let's start thinking about what activation energy means. Activation energy you can think of as an energy barrier or an energy hill that the collision has to overcome on its way to product. So think about driving or walking, and you're walking up over a hill to get to another location. Okay? If we look at this energy diagram here, the activation energy, energy of reactants, energy of products, activation energy is a hill. Now notice here that products are lower in energy than reactants. So this reaction overall releases energy. This is an exothermic reaction. Okay? Now, linking this back to atomic level events, we know that they have to collide to react. And now we can say they have to collide at the right energy to react. And the next thing we have to say is not only do they have to collide at the right energy, they have to collide at the right location. A, okay, represents the number of approaches to the activation energy per unit time. It's an alignment factor. Okay? Now, as temperature goes up, the number of collisions per unit time goes up. And as temperature goes up, okay, the percentage of collisions above the activation energy go up. Let's look at this graph. Now, here at T1, which is the cooler temperature, you have the distribution, the fractional distribution of the molecules and their energies of collision. At the higher temperature, notice I get a wider base, okay, and the average energy of collision is going up. Now this little area right here, that's the portion of the collisions at T1 that are above the activation energy. Notice at T2 we have a lot more collisions above the activation energy. The more collisions you have above the activation energy, the faster the reaction is going to go. The other thing I want to point out is not all collisions at the right energy are successful collisions, because remember they have to be aligned correctly. Okay? Now, practice problem 14.7 on page 609. Okay, there's the original K. Here's another version of Arrhenius's equation that you can use. And there's the third. There are two problems here that are just plug and chug. I think you can handle them on your own. Okay? Two theories that try to explain how things are happening on the atomic level. One is called collision theory. The other one is called transition state theory. And they're side-by-side theories because they explain different parts of the molecular event. Okay? Collision theory says that reactants, ions, atoms, or molecules, must collide to react. The possible number of collision combinations per unit time set the upper limit on how fast a reaction can happen. And to have a successful collision, the particles must collide at the right location and with the right energy. So, energetic collisions could lead to products. Collisions that aren't at the right energy don't lead to products. We also have to have collisions, of course, at the right location. Okay, so ineffective collision, effective collision. Notice it's all about how they're aligned. Okay, that A factor has two parts to it, ultimately. Z, a collision frequency, how many collisions you're getting per unit time, and a complexity factor. Now, we're going to restrict ourselves to our discussion right here of collision theory to talk about simple one-step reactions. And what I mean by one-step reactions is that the reaction actually happens as a single collision event. Most reactions on the atomic level are actually a cascade or series of collision events to actually get from reactant to product. No matter what it looks like in the chemical equation, the atomic level doesn't care. It may go through multiple steps to get us where we want to go. Okay? So if we had a single collision event, A plus B going to C, and we were to look at how the concentrations multiplied together in the rate law, we did it experimentally, we would find out that it would be related to the number of possible collision combinations. So if I have 2A and 2B, there are 4 possible collision combinations. If I had 3A and 2B, there would be 6. And if I had 3A and 3B, there'd be 9. So notice, 2 times 2 is 4, 3 times 2 is 6, 3 times 3 is 9. So if it happens in a single collision event, then the concentrations of the reactants just multiply together to help us determine the rate. Okay? A single collision event. We're looking at something very simple. So the reason that concentrations in a rate law are multiplied together is because it's linked to the number of combinations that will ultimately control the upper limit of the rate of the reaction. And this is for really simple single collision events. Collision theory was based on single collision events. This goes hand in hand with transition theory. Transition theory describes the moment of a collision at the right location and the right energy. When you have a collision at the right location and above the minimum energy, you still only have a 50% success rate of conversion from reactant to product. Because when it's at that top, that highest energy point in the collision, potential energy point, it has a 50-50 shot of going either direction. So let's look at a molecule at that collision point. Okay? It's going to have partial bonds. It's going to be a molecule that's neither reactant nor product. It's something in between. We call this a transition state or an activated complex. It's going to last for something like a femtosecond, 1 × 10⁻12 seconds or less. It's unstable because it has all these partial bonds, and we can't trap it. Now, they're using laser pulses to look at these things so they know more about these partial bonds, but it's really wild stuff. Okay? Now, very, very unstable, can't be trapped. So let's look at this image right here. In the beginning, okay, the molecules are very far apart and they're moving toward each other. As they start to get closer to each other, their electron clouds repulse. So they start to slow down. And we start to have a buildup of potential energy because they have the potential to push against each other. And as they get closer, okay, we start to form partial bonds. The original bond here is starting to elongate, and there's a bond that's being reached out and starting to form here. Okay, guys, we're entering the last section of chapter 14, which is reaction mechanism. And this is what kinetics is really all about, is being able to predict a sequence of collision events that make the overall reaction that we see when we write a chemical equation. Now, each single collision is represented by what's called an elementary step, which is a chemical equation to represent that single collision event. Okay? So we're trying to work out the atomic level happenings of a reaction. If we were to develop a catalyst, if we want to develop a catalyst or a new reaction scheme, we've got to understand the blow by blow of the chemical reaction to be able to effectively create a catalyst or dream up a new scheme for making a product. If we had a reaction 2A plus B going to E plus F, it might happen in a set of steps. An A plus a B going to C, an A plus a C going to D, and then a D decomposing into E plus F. Each one of these steps is a single event in the overall process. C here, okay, is made in step 1 and it's used up in step 2. D, give it a different color, made in step 2 and it's used up in step 3. Both of those are what we refer to as a reaction intermediate. It's made in an earlier step and it's used in a later step, and it's not in the overall reaction. These molecules are stable, okay, and can sometimes be detected in the reaction chamber, which is very important in us determining if a reaction mechanism is the real thing or not. So reaction intermediates are real molecules with real bonds, and we can sometimes isolate them. Okay, when we're looking at reaction mechanisms, we want to prove what that mechanism is, and the ultimate proof is to isolate an intermediate. So one more time, each step in a reaction mechanism is called an elementary step. It represents a single molecular event. That could be a collision, that could be a molecular rearrangement, that could be a decomposition. Okay, an elementary step cannot be composed of simpler steps. An elementary step is characterized by the number of particles involved. A unimolecular step, okay, involves one particle. A bimolecular step involves two particles. A teramolecular step involves 3 molecules interacting, and that's very rare. Because think about trying to get 3 things to collide at the right energy, at the right locations. Pretty hard to do. The maximum number of molecules you can find involved in any single collision event is 3. Okay, and again, that's very rare. It's usually unimolecular and bimolecular. Although we can deduce the rate law, we can't deduce the rate law for an overall reaction based on the coefficients in the balanced chemical equation, because ultimately that equation is made up of individual steps at the molecular level. We can determine the rate law for an elementary step based on its equation, its chemical equation. The rate law for an elementary step, and for an elementary step only. Notice I highlighted and underlined that. I bold-faced it. Okay, I highlighted it. For an elementary step only. Again, be determined from the coefficients in a balanced chemical equation for the single collision event. Okay, at the heart of that is the fact that the elementary step represents a single collision, not an overall process. So let's look at some examples here. If I have A going to product, it's unimolecular, and the rate law is going to equal K times A. If I have A reacting with A, it's bimolecular, and the rate law is going to be K A squared. If I have A plus B going to product, then the rate law is K A concentration B concentration. If I have A, 3, rare, okay, you can see the pattern. So let's look at some examples of a multi-step process, and we're going to write the rate laws for each one of the steps. Now, if we look in your book and we look at problem, let's see. Come on, I want a nice elementary step setup. Okay, let's look at the following. Now I'm going to flip this around so we got the screen. Let me tap. Okay. So there's the screen. Move it back a little bit. Let's write on it. We have a 2-step process. Nitrogen dioxide plus nitrogen dioxide going to nitrogen trioxide and a nitrogen monoxide. Okay, this is step 1. Step 2 in this reaction mechanism is nitrogen trioxide reacting with carbon dioxide to give us nitrogen dioxide and a carbon dioxide. Okay? Now, if we add these together, we'll get the overall reaction. So notice that a nitrogen dioxide here, okay, and a nitrogen dioxide here are on opposite sides of the arrow. They'll cancel out. The nitrogen trioxide here and the nitrogen trioxide there are going to cancel out. That's a carbon monoxide. So if I add these two together, I get nitrogen dioxide plus carbon monoxide goes to a nitrogen monoxide and a carbon dioxide. This would be our overall reaction. Okay? Now let me make sure that that's all showing up. Right, so there's our step 1, our step 2. Okay? That's a reaction intermediate. And you can cancel those two out. I don't know if you call them a reaction intermediate or not. but they cancel. Now, if we look at that very top reaction, okay, and I wanted to write the rate law for that reaction, I would just write, and here, let me sit this down. For the first one, for number 1, rate 1 would be K, concentration of NO2 squared. Okay, for the bottom one, rate 2, that's rate 1. Rate 2 would be a constant K2 times the concentration of NO3 times the concentration of CO. Okay? Make sure we got that. So there's rate 1 based on that equation. And here's rate 2 based on that chemical equation. All right? Okay. Now, anytime you're given steps in a mechanism, then you can write an overall reaction for it, and you can write a rate law for each step. So you can look at like example 14.9 in your textbook. Okay, let me give you another example, and I'll try typing this one, and we'll see how well I can type today. So we've got ozone, O3, plus, well, going to O2 plus an oxygen. Okay, and everything's in the gas phase. I'm going to be lazy and not put in the, and this is step 1. Now the rate law for this would be rate equals K, the concentration of O3 to the first power, because there's only one O3 there. Okay? Our step 2 is given as O3, and I'm going to be lazy. Oh. Plus an oxygen. Why is that? Going to 2 O2s. The rate here